So this is a second video about propagating uncertainty in fluid inclusion barometry, and this uses the data from Data Natal 2023 in Science Advances about the Palma eruption. So what we have here is probably a pretty typical data frame that you might have. So we've got the file name, this is the name of the fluid inclusion. We've got its density in grams per centimetre cubed. And then we have the EPMA analysis of the host olivine. And on the right-hand side here, we have the forced dry content that's been calculated. So say we want to work out what pressure and what depth these fluid inclusions came from. So what we're going to do is you're going to download this notebook as normal from Read the Docs. And then you're going to import your standard Python packages. And then we are going to load this data frame in. So we give it the name of the Excel spreadsheet and we get this beautiful data frame. And you can look at the bottom or the top of this and you can see all of the column headings. So to start with, we might just want to visualize the distribution of our densities. So we can do that here using the simple histogram function. And you can see that the densities range from about 0.75 to 0.97. Okay, so what pressures are these? In the previous video, I showed how you can convert this into pressure and depth without the error. Here, we're just going to go straight in and dive in doing the full Monte Carlo simulation because it's nice and quick. So we're going to say that we have a temperature of 1150 Celsius. The error on that is 50 Kelvin. We want that error to be an absolute error because the unit's Kelvin, not percent. We want it to be normally distributed. And then we have the CO2 density that we loaded in, so that is the data frame. And then the column heading is this, which is why we've put it between square brackets with quotes. From repeated measurements of a single fluid inclusion at these densities, this is a good 1 sigma error. Again, that's an absolute error that's distributed normally. And then what we want to do is we want to use a 2-step density profile where we have a density of 2,800 grams per centimetre cubed above 14 kilometres and 3,100 below that. We are using that density profile to calculate a depth, but we are not propagating any uncertainty in that. We have not specified an error for crustal density. And that's because realistically, this is going to be a systematic error at this point. It's not easy to do this as a normally distributed error in this particular scenario. We're saying we want 1,000 duplicates per fluid inclusion, and we want to plot the figure for the first sample to look at what the simulation looks like. So you can see it just prints what sample it's on so that you don't lose patience. It's pretty fast though, so I don't think you're going to have to worry about that. So for the first fluid inclusion, this is what the distribution of temperature of the input looks like, the distribution of CO2 density, and then we're not propagating any error in crustal density. So this is the distribution in depths, in kilometres, in pressure, in MPa, and pressure in kilobars. So you can also inspect that. So you can see the average we have for fluid inclusion 1. This was the density that was measured. This is the depth that is calculated from that density, no simulation involved. This is the pressure that is calculated from that density, no simulation involved. And then if we actually do the Monte Carlo simulation, this is the mean of all of the Monte Carlos, and you can see it's very, very similar. It's only different on the 4th number. The median of the Monte Carlo, the standard deviation, and then you've got the mean, the median, and standard deviation in depth as well, and then you've got all the different input variables that were supplied to this. So we can also look at the all. So this is basically the simulation for every single fluid inclusion. So there are 1,000 rows times by however many fluid inclusions you had. So that can be useful for plotting. Now what we want to do is we've got 4 different samples. So we are going to want to plot the fluid inclusion pressures and depth for these samples. Now, you can get a logical for each of these. So what we're basically saying is we want to know the rows where sample equals 0. And you can run that. And you can see what that looks like is this SAM 0. This is a set of true, 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 false. So what you can now do is you can apply this true, false column to your data frame. And now you will only get the rows where the sample is 0. So you can see all the way down here, the sample is 0 in every single one of these. And this can be used for plotting. So for example, say we want to get the X column, the force rate for sample 0. we could do it like this. So what are we doing here? We're making a figure. So it's a 1-part figure, and this is the figure size. We're then going to plot sample 0 with an error bar. So we're going to plot the x coordinate is force right. The y coordinate is that single fluid inclusion depth in kilometers. The x error is 0. You could put an error on your force right content if you want. It just depends whether it's going to clutter up the plot and whether you think it's important. Then the y error is the standard deviation from the Monte Carlo simulation in kilometers. You're then saying you want a circular marker with a black edge. You want the error line width to be 0.8. You want the marker face color to be red, and you kind of want the, this is the error bar color, and these are the colors of the markers and their size. So that's for sample 0. For sample 1, same, but we're going to use a triangle marker instead, which is green. For sample 4, we're going to use a V-shaped marker, which is blue. And for sample 6, we're going to use a square marker, which is orange. And then you're going to label that you've got force right content and depth. Traditionally, depth actually increases downwards, not upwards, so we're going to invert the y-axis. And then we're going to make a second axis for showing pressure alongside. So what we're going to do is we are going to use a pressure limit of 3.8 and 8.1. And we're basically going to set our y limit here as these two pressures. And then we're going to basically convert pressure to depth using this function because we want to know how we align that axis with a pressure axis. So you can see here that we actually wanted depth on the first axis, that's AX1, which is what we plotted our depths on. So we're basically going to set this to the limit of what we calculated were the corresponding depth values for those pressure values. Now, obviously, this is a 2-step profile, so that axis will actually be non-linear. That can cause complications. You'll have to overcome those, except here we are working consistently below that depth transition. So in terms of the pressure limits we wanted and the depth limits, we don't need to worry about that transition at 14 kilometers. So we can run this, and you basically get a color for each of your samples, and you get the error bar, and you get the pressure, you get the depth, and you get the force right content. So that can be a useful plot.